Okay, problem number 5. This one is very similar to problem number 4. We're calculating the thermodynamic properties and statistical properties for a chemical reaction. H2 plus Br2 goes to 2HBr, but this is a somewhat more complicated reaction. It's not just atoms on the reactant side, it's actual molecules, so the calculation will be a little bit bigger and a little bit more representative of the way most calculations are for chemical reactions. The temperature is 298.15, the standard state pressure is 1 atmosphere, which means that once again I've chosen table conditions for this calculation. The change in mole numbers is 0 between the two sides, so that means that our equilibrium constant Kc will be the same as a Kp, and we don't have to do any conversion like we did in the last problem. Again, the problem is to find, first of all the factors, all the contributions from all the internal motions for the equilibrium constant, and then to calculate, using that equilibrium constant and other things, to calculate all the thermodynamic properties we can think of. As before, we'll need data, a little bit more data this time, because there's 3 different kinds of molecules, and they all have vibrations and rotations. It's useful to look at some of these numbers. Of course, the very high vibrational temperature for H2 means that the vibrations basically don't do anything. There's also a very high vibrational temperature for HBr. That's because, of course, it's got this hydrogen on there. One light atom makes for fast vibrations, and likewise, one light atom makes for a relatively small moment of inertia, so it's got a relatively high rotational temperature too, and of course H2 has the highest rotational temperature of anything. But then Br2 isn't quite as heavy as I2, but it's still very heavy, and so it has relatively low vibrational temperature. That means the vibrations of Br2 will contribute, and a quite low rotational temperature too. In the original version of this problem, as it was written up and put out in the practice exam to begin with, these numbers were a little bit different. These D0 values were a little bit different. I got values in my calculation that didn't agree very well with the table, and it's taken me some time to figure out where the issue was. It turns out there was a bad number in the source. I got these numbers from another textbook, and apparently there was a bad number in that textbook, so I've corrected that now. And that doesn't mean that the old key was wrong, it just had a bad number, and now I've corrected that. So now the calculations agree quite well with the values from the tables, with the equivalent calculations from table values, but I won't do those comparisons since they weren't in the original key and I didn't want to make that many changes. All right. So this calculation will be very much like the last one. Let's just go through it. First of all, we want to get the value for the translational contribution to the equilibrium constant, Kt. We have our nice formula for that, 0.46009 T to the delta N power. Molecular weight for HBr squared, right, because there's 2 of them. Molecular weight for H2, molecular weight for Br2. And then all of that to the 3/2 power. Delta N is 0 here, so none of that matters, it contributes anything. This becomes just molecular weight for HBr is 80.91 squared divided by 2.016 and 159.8. all to the 3/2 power, and that turns out to be 91.60 for the contribution from translations. Notice that that's still, well, it's not as translational contributions go, that's a rather small one, but it's not a 1. It's the translations are contributing something in this case, and that's because in this case we have H2 plus Br2 goes to 2HBr. And so this is a very light molecule. Its translational partition function is fairly small as translational partition functions go. The Br2 should be big, but there's only one factor of it, right? There's only one Br2 molecule. And each of the two HBr's is also pretty big, but there's two of them. That gives rise to this molecular weight squared up in the numerator of our KT. And so the translational partition functions on the product side here are bigger and outweigh and win over the two translational partition functions on the reactant side in this case. It's just worth pointing these things out as we see them so we get a feeling for why numbers that we're getting are what they are. Next is the rotational partition function. That's going to be Q rotational for HBr squared over Q rotational for H2, Q rotational for Br2. I put a bar on there, but there really shouldn't be a bar there. That is equal to, these are all diatomic molecules. The symmetry factor for HBr is 1, so this is T over theta for HBr squared over T over theta for H2 with a sigma factor of 2 in there, times T over 2 times theta for Br2, again with a sigma factor of 2 in there. That is equal to 298.15 over theta for HBr is 12.02, quantity squared, over 298.15 over 2 times 85.3 for the theta for H2, 298.15 over 2 times 0.116 for the theta for Br2, and plugging in all the numbers. It's worth pointing out, notice that there's two factors of 298 on top, but there's also two factors of 298 on the bottom, so those actually cancel out in this case. That's a consequence of delta n equals 0. When delta n equals 0, there's lots of consequences throughout the calculation, and so I thought I'd just point that one out. So it's really just the ratio of the rotational temperatures here. The actual temperature doesn't matter at all. And that comes out to be 0.2739 for the rotational contribution. Notice that means that the rotations are a little reduced on the product side compared to the rotations on the reactant side. And so in this case, the rotations are unfavorable towards the reaction. Next is K vibrational, which will be Q vibrational for HBr squared over Q vibrational for H2, Q vibrational for Br2. The only one of these Q's that's going to be anything other than just 1 is the one for Br2 here. These guys, we'll plug into them just for rigor's sake, I guess, but we know they're going to be basically 1. And even the one for Br2 isn't going to be that different from 1, but it will be at least significantly different from 1. All right, so plugging in, I'm going to need more space, so I'm going to go down to the next line. This becomes R times theta vibrational for HBr, e to the minus theta vibrational for HBr. Sorry, that's wrong. I'm defaulting to energy calculations here. So the Q vibrational partition function is 1 over 1 minus e to the minus theta vibrational over t, right, always. So this is going to become 1 over 1 minus e to the minus theta v for HBr over t, quantity squared, over same thing for H2, and for Br2, And plugging numbers in and doing that calculation, that's actually all over here on the other side. So here it all is on the other side. I won't plug in the numbers in this case since I think it's pretty obvious. That turns out to be 0.7884 for the contribution from vibrations to the equilibrium constant. Notice that means that, again, the vibrations are just slightly unfavorable to this reaction. The vibrational contributions, so here's H2 plus Br2 goes to HBr, two HBrs. These vibrations are fast, of course, have a big gap between levels. That's true for this one, too, because of the hydrogen there, which gives rise to a small reduced mass and a fairly large force constant, so a high vibrational frequency. So the main contribution to the vibrations is from Br2, which is the only case where you've got a soft bond and heavy molecules. And so when you go from reactants to products, you're losing a little bit of vibrational states, and that's why this contribution is a little bit unfavorable. All right. That's the vibrational contribution. The electronic contribution is just ground state degeneracy, so that's W0 for HBr squared over W0 for H2, W0 for Br2, but those are all ones, and so the electronic contribution is just one. The last thing we need to compute is the ZPE factor, or the bond energy factor, and that is equal to e to the minus, looking up at the table here again, 2 times the D0 for HBr, well, minus 2 times the D0 for HBr, plus the D0 for H2, 432, well, let's just write it here, D0 H2, plus the D0 for Br2 over RT. Notice that there's a minus sign on all of this, right? Delta E, ZPE, is equal to minus delta D, 0, right? Where the delta here indicates a products minus reactants difference. And so that's why there's a minus here, a plus here, and a plus here, rather than the usual thing, which would be a plus here, a minus here, and a minus here. It's that minus sign right there. All right, so plugging in numbers, that's e to the minus 2 times 363 minus plus, what is it for H2? 432 and 190 are the other numbers I need. 432 and 190 divided by RT, which is 2479 at 298 K. And that turns out to be, when everything is said and done, these have to be multiplied by 1,000. Sorry about that. These are in kilojoules per mole. This is in joules per mole. So we need to convert these top guys to joules per mole. So we got to multiply them all by 1,000. Anyway, the net result is e to the 104,000. So the net delta D is minus 104,000 over 2479, and that is equal to 1.658 times 10 to the 18th. So again, as usual, the ZPE factor, or the bond energy factor, dominates, is by far the biggest factor in this whole calculation. Putting everything together then, K, and this is again Kc, though it's the same as Kp for this particular case, Kc then is 91.60, that's the Kt factor, 0.2739, that's the Kr factor, 0.7884, that's the Kv factor, and finally 1.658 times 10 to the 18th Sorry, there's a 1 in there. Doesn't do anything, but let's put it in. That's the Ke factor. And then finally, this is the ZPE contribution, or the bond energy contribution. And multiplying all those together gives you 3.280 times 10 to the 19th. Did I mention above? I don't think I did, but in the original source, there was a bad number here. And so all these numbers that I'm getting now are a little different from the numbers that I got in the original key. So if you got different numbers in your original calculations because you were following the original homework assignment, well, I apologize for any trouble, but your numbers are still probably right given the numbers that were in the assignment. These new numbers are just with that better number. They agree more with the table. All right, then we have Kc. From Kc, now that was all of part A. Now part B, the very easiest thing to calculate is delta G for reaction. That's minus RT log of Kp really, but that's the same thing as RT log of Kc in this case. And that is equal to minus 2479 log of 3.280 times 10 to the 19th, which turns out to be minus 111.40 kilojoules per mole. Again, this I won't calculate it actually, but if you do the calculation from the tables, that value agrees now pretty well. And this is the first value that we've been able to compare to the tables, right? We really don't have an equilibrium constant to compare, but we do have a delta G value that we can compute from the tables, and that does agree now. Closely, anyway. I think the value from the table is about 110, so we're off just a slight bit, but not very far. It was off by 30 kilojoules per mole before. There was obviously some problem. And I thought I made a mistake in the calculation, but I couldn't find one. Eventually, I found a bad number from one of my sources. All right, so delta G. Now delta A, remember, delta A is equal to delta G R0. Let's rederive it because I can't remember the number, the relationship either myself. Delta G is equal to delta H minus T delta S, but delta H is equal to delta U plus delta PV, and then minus T delta S. Delta PV is delta nRT for this case. And delta U plus T minus T delta S is delta A, so this is delta A plus delta nRT. Delta nRT is 0 in this case, right, because delta N is 0, and so delta G is equal to delta A. And therefore delta A is equal to minus 111.4 kilojoules per mole, just like delta G. Okay, what next? Let's follow the key and calculate delta U next. That's one that requires some calculation. We can't get that quickly from the numbers we already have. So, as before, delta U of reaction has its own contributions from translations, from rotations, from vibrations, from electronic degrees of freedom, and then in this case, as with all chemical reactions, there's also a ZPE contribution that we'll have to calculate at the end. And as we've seen with the equilibrium constant, this ZPE factor turns out to be the biggest thing, though all the other contributions are significant too. Well, some of them are anyway. First of all, delta U for translations, let's just look at the reaction. That's H2 plus Br2 goes to 2HBr. There's two translations on this side, two translations on that side. For energy, the translations all contribute the same amount, right? It's 3/2 nRT. And since there's equal numbers on both sides, they're all going to cancel, and that's going to give 0. You can prove that formally if you like, but you can see the logic behind it even without doing the math. Delta U for rotations is also going to be 0 for the same reasons. We've got one linear diatomic here, one linear diatomic here, two linear diatomics on the reactant side, two linear diatomics on the product side, which means since all linear diatomics have the same contribution, that those are also going to cancel. So those two are easy. Now for the vibrations, we actually need to calculate differences. So first, there's going to be two contributions of the U for vibrations for HBr, then a contribution minus a contribution on the reactant side of vibrations for Br2, and the same thing for H2. So just going down the list, first of all, the energy of vibration for HBr is equal to R times the theta for HBr times e to the minus the theta for HBr over T over 1 minus e to the minus theta for HBr over T. I won't plug the numbers into that. Let's just give the result. If you do plug the numbers in, we know the theta for HBr. We used it up above, in fact. That's 0.1918. I'm copying this from the key over here. That's that number right there. That's a pretty small contribution given that, what's coming up here from the ZPE factor is 104,000. Here's not even 1. So that's pretty negligible, but anyway, we did it, we calculated it. U for vibration for H2, we already know that's going to be negligible. I didn't even calculate it over here on the key. You can see here, I said it's about 0. I don't even know what order of magnitude it is right now, but we're going to neglect it no matter what it is. Then the U or the contribution from Br2, that should not be negligible. That's got the lowest vibrational temperature of anything in this problem. So it should be the biggest contribution of all, and let's see how big it is. Same formula, just different numbers. The numbers for Br2 rather than HBr. And that's 8.314 times 463, way up here, 463 for the vibrational temperature, times e to the minus 463 over 298.15, 1 minus e to the minus 463 over 298.15. You can see that the vibrational temperature for Br2 here is getting close enough to room temperature, so this ought to have some, well, little bit of a contribution anyway, and in fact what we get is 1033.3 when the numbers get plugged in. So between these two, it's a total of about 103.5. You can see this really is, this guy up here, the HBr contribution really is negligible. Actually, sorry, this number is for twice. It's for both of these two contributions for HBr. Anyway, it's still negligible. But I put it in anyway, what the heck. Finally, the ZPE contribution is minus the delta D0 value for this reaction. That is equal to minus 2 times the D0 for HBr minus the D0 for H2 minus the D0 for Br2, and plugging the numbers in, that's minus 2 times 363, if I remember right, minus 190 for Br2, and what is it for H2? 432, is that right? I have to go look. Let's see if it's 432. 432, good, okay. And that is equal to where is it? Minus 104.00 kilojoules per mole. Notice this is in joules up here. This is only 1 kilojoule. So altogether, delta U reaction is equal to 1033.3 minus 104,000, which is equal to minus 103,000, well, minus 103 kilojoules per mole. And yeah, the 33 here is just below the significance, so it doesn't even count for delta U. Obviously, this is dominated by the bond energy contribution, as has been usual throughout these calculations. All right, that's delta U. Delta H in this case is equal to delta U plus delta PV, right? That's from the definition of delta H. This is delta nRT in this case, but delta N is equal to 0, so delta H is equal to delta U, and it's also minus 103.00 kilojoules per mole. That was easy. The last thing is delta S. Let's derive that from delta G like we did in problem 4. Delta G of reaction is delta H of reaction minus T delta S of reaction. Therefore, solving, delta S of reaction is equal to delta H minus delta G over T. So now we have all these values we just have to plug in. Delta H is minus 103,000 in joules. Minus for delta G, that was minus 111.4, is that right? Yes. 111,400, that is, divided by 298.15, and that gives a value of 28.17 joules per K divided by per mole. And that is it for our calculation. I once again didn't compare any of these calculated values to the table values, but they all come out reasonably close. They're not as close as with the last example in problem 4, and probably the reason is that for some reason the numbers are less reliable. The input numbers, the data numbers, are less reliable for this calculation than they were for the last one. I don't think the calculation is really seriously off. I think some of the data going into the calculation is off, a little bit further off. We still get good agreement now that I corrected that one table number, though. All right, we'll do number 6 next time.